Good afternoon, everyone. The quiz class of MCMT would like to discuss regarding the concepts related to the machinability and the factors which are affecting the machinability. Let us discuss what is the meant by machinability is. So nominally the processes of work material with different factors for the necessary dimensional occurrence is considered in many ways, as far as the milling, drilling, reaming, boring process, and lathe machines such as turning process and various methods related to turning process, knurling, stepwise cutting, and facing operations can be performed. And the major parameters to be analyzed in the case of machinability in a deep journal will be discussed in today's class. Machinability is nothing but shaping the material by the discussed processes with the help of the cutting tools which are having prescribed towards them. The machinability of a material is in depth discussed or defined with respect to the parameters such as the high surface finish, the tool life, force and the power required for the MRR process with the help of the tool, which will be calling the machining process. The level of difficulty and chip control. By these four different parameters, and even some more parameters such as speed, depth of cut, etc. will be accessed. But when compared to those, if these four parameters are considered to be having the good machinability, which leads to a high surface finish and integrity, increasing in it with respect to its tool life, less force is sufficient for performing the machining operations, and even the power requirements coming to the index of this machinability. Due to many of the complex natures in the case of this cutting operations, it's very much to have the relationship that quantitatively define in a particular material. Even it relates to a perfect dimensional accuracies with respect to the input parameters given and compared with respect to the standard dimensions that are existing in the historical rates agitation. Hence, the machinability rating of a material leads to in quantifying the machinability of various materials, where quantifying of machinability K is equal to V60 by V60R. where that V60 is the cutting speed of the target material. It gives the tool life of 60 minutes, and V60R is the same or reference with respect to the material. Hence, these reference materials which are selected for the group of working materials, that too within the ferrous and non-ferrous. Both the associations can be considered. And among them, the popular materials, branded materials will be utilized. So here the branded leads to the demand-oriented materials such as quality and quantity maintenance. And reference materials leads to that indeed to machine on the plastic materials or else less ductility materials, less carbon content materials or enough as a tool materials. If at all the hardest materials need to be machined, concerned materials which are more harder than the existing materials will place a major role that high ferrous content of materials. Hence, if Km is equal to 1, the machinability of target material is better than that of the reference material. And if at all it is less, and poor results will be declaring as an output. And even we have to note that the system is misleading because of the index is different for different machining processes. Hence, here index specifies that the total machinability characteristics that are being given as an input to the materials or machinery process is related to the machinability index. So indeed to get the a better results when compared with respect to the reference materials, then the quantifying of machinability on various materials, whereas the Km should be greater than 1 when targeting on the material by machining process. Coming to one of the example over here, if the reference material is the steel AISI American standards 1112 steel has an index of 1, it clearly specifies that machining of the steel with some parameters, cut speed, feed, and the depth of cut, that the cutting speed maintained is 0.5 meters per second and giving the tool life of 60 minutes. Therefore, V60R will be referred to 0.5 meters per second, and for austenitic 302 SS steel, the machinability index Km is equal to 0.23 by 0.5. That 0.23 referring that the tool life for 60 minutes is reaching at 0.23 minutes per second. So the cutting or machinability rating, the amount of material per minute or per second that is being removed by that SS steel is 0.23. That too for AISA 1045 steel. Simultaneously, for the tool life of 60 minutes, when it has been reached at 0.36, then we'll be having the resultant as 0.72, as 0.36 by 0 cutting speed, that is 0.5 meters per second, leads to a 0.72. Hence, there is a clear-cut expression comparison with respect to one result to another result based upon the material change. As such, AISI steels 1112 is greater than 1045, and hence 1045 is greater than the 302 SS. Have to be beware that the tool life cannot be considered only on the criteria of machinability and its index factors such as cutting velocity, and by considering some of the limitations, this machinability is defined as the ability of being machined and more reasonably as ease of machining. So that will be calling that the ability of removing the material from the work part with the help of the tool, that to more efficiently and reasonably within the nominal calculations, which is leads to an ease of machining. Hence, the removal of the material with respect to the particular tool which is being worked on it leads to an ease of machining. Come to the machinability factors, the factors which are considering for the removing of the material or the machinability. That is work material aspects that will be of various parameters because of various factors. First one is the work material aspects. Secondly, the cutting tool aspects. Third one is the process parameters aspects and machining environments aspects. And in detail, we'll be looking after one by one. Coming to the point of this work material aspects, the properties which are governing the machinability or these work material aspects are listed below. First one, the nature of the material, whether it is a brittle material or else the ductile material, which leads to nominally the machining or force applied that will be confined to high rates, high strength to weight ratio, and the microstructure, that is nothing but the statistical data or structural data of the material and its course, and even the tensile strengths and the yield stresses, hardness, hard strength and hardness. Listen, work hardenability, thermal conductivity based upon the frictional forces which are creating in between the tool and the work part. The thermal stresses will be produced. So the conductivity leads to a formation of those thermal stresses, leads to a temperature increment at the frictional area. Chemical reactivity, upon reaching to an high thermal stresses than the resistible ranges, but it has been having a capability of reactance, then the chemical reactivity is one of the property that leads to changes over the machinability, stiffness, or self lubricant. So, in order to reduce the thermal stresses producing during the meshing process, nominally we will be following or utilizing the lubricants either in the minimum quantity or else in the maximum quality as per the materials requirement during the cutting process. So the stickiness places that high friction or high viscous generation in between the tool and the machinery, sorry, work part or the machinery in the process. So these are the parameters will be governing or resulting the machinability, that too over the work material aspects in the point of this work material. Let us discuss one by one in detail. Nature, brittle or ductile. Brittle materials are very much easy to machine, and the separation of this chip because of its less tensile strength and even having the less frictional force generation and heating at the rack surface at the mating point of the tool tip and the work part. Hence, it leads to a formation of mini chips elevation over the MRR process. Even these ductile materials like mild steel, cast iron, this produces high surface finishing because of the BUE technique. If at all this BUE is being formed, hours of surface finish will be deteriorating. That is nothing but rough surface finishing will be achieved. And even upon increasing the cutting forces, the yield shear strength also will be getting increased, and hence the work material microstructure will be getting changed and getting altered due to the high forces that are cutting forces are generating, and even deteriorating the surface finish because of the formation of this built up edges. So large chips will be getting elevated over this ductile materials. Hence, the value of the shear strength and shear force of a given material is directly depending on its microstructure itself. As we have been discussed, that they will be having 14 different Bravis lattice structures, and each and every material will be existing the microstructure related to those 14 structures. And depending upon these parameters, that microstructures will be getting varied. And it leads to a less value of TS as it is reduced maybe by the heat treatment process such as annealing or else the nitriding process, normalizing conditions, etc. For the steels, which are controlled by adding the materials such as the sulfur, lead, tellurium, cadmium, etc., which leads to a free cutting of the ductile materials and its alloys. Coming to the point of this hardness, hardened materials, which are obviously very much difficult to be machined, upon increasing the cutting forces, it will lead to a damage of the tools and even the surface finishing of the objects also. But usually we'll be utilizing the incrementing in the cutting velocity and its forces will be getting decreased towards some extent. Upon increasing of this cutting velocity, the cutting forces will be getting decreased and hence it will be having a reduction in the TS and also the chip thickness. And thermal stresses also will be getting decreased. Thermal stresses also will be getting a decrease due to the softening of the work material, particularly at the shear zones because of these elevated temperatures. Hence, because of this increasing temperatures and cutting velocities, and even when working on the materials such as hot, strong, and hardest materials such as the nickel, titanium, based on these super alloys and work hardenable uh, high manganese steels and alloy materials such as nickel and hardness materials, nickel, manganese, titanium, and next towards magnesium alloy combinations. And this will all or will be having a bit difficult and will be getting accessed only by increasing the cutting forces. Obviously, it leads to an high frictional forces inducement and increases the temperature and its cutting velocity. Coming to the point of the stiffness or self-lubricity, sticking of the materials and the formation of this built-up edges or the tool surface that hamper the machinability by increasing the frictional forces and cutting forces and even the temperatures. Surface roughness is also will be getting increased. Coming to thermal conductivity, it lowers towards the work material and affects when it is raising the cutting zone temperature, and hence it affects on the tool life, hence it will be getting cut off. Coming to the point of this cutting tool aspects. So part material aspect we haven't discussed till now, and proceeding towards the cutting tool aspects. The tool life is estimated or imagined mainly by the tool material itself, which is influences with respect to the cutting forces and the temperature. Apart with that, the accuracy and finishing of the machined surface. Hence, previously we'll be utilizing for a medium range of objects. This normally HSS materials will be utilized in order to get compensated with respect to the elevated temperatures. The coatings such as ceramic coating and sintering with respect to the carbide will be getting monitored over the tip of the tools for increasing the tool life. Hence, the properties such as strength, hardness, toughness, wear resistance, thermal conductivity, it plays a major role in the machinability characteristics. and high wear resistance and stability towards the chemical agitations of the cutting tools, which generally will be utilizing in our machinability machining processes such as carbides, ceramics, cubic boron nitrates. These helps and generate a better surface finishing and high machinability agitation will be conducted. It leads to less frictional force creations, and even cutting temperature also will be reducing to a maximum extent because titanium can be cope up and resist with respect to temperature. And the formation of this built up edges will be occurred and when the cutting forces or cutting speed has been increased for the steels. This machinability is affected by the geometry elements such as rack angles, the clearance angles, and the nose radius with respect to tool and the work part materials. When the cutting force has been initiated, the performance of the tool with respect to an angle of gamma that increases in the rack angle reduces the cutting forces. So upon increasing the rack angle, simultaneously the cutting forces will be getting dropped down and the chip load will be getting elevated even by decreasing its strength at the tool tip. And this leads to a high frictional resistance during the machining point and the tool life will be decreasing. And inadequate clearance angles that reduces the tool life. This is one of the defect in the case of this cutting tool aspects, as the surface finish by this tool rubbing and a too large clearance also will be the results in the reduction of this tool strength and even the tool life also. If the strength has been decreased, it is directly proportional towards the life of the tool. If the proper nose radius has been maintained, it will be increasing in the machinability, and through that, the life of the tool also will be increasing by increasing its mechanical properties such as strength and its stiffness that resist with respect to a generated temperature because of the frictional forces that are being produced at the point at the tip that reduces the surface roughness also, and hence will be achieving the good surface finish upon machining conditions. Coming to the process parameters, the proper selection of this cutting forces, feed, speed, depth of cut, nominally it will result in a good machinability characteristics. And even the MRR condition also will be progressed and will be achieving the better dimensional accuracies for the work part. Among these parameters, the depth of cut is the least significant role because almost all nominal depth related towards the cutting process will be provided by the external offense to the tool. When the cutting velocity has been increased, it leads to a reduction in the tool life. that reduces the cutting forces. Automatically, it will be resulting in the case of the surface finish by the favorable chip tool interaction. Even some of the tools, especially the ceramic tools, perform better and longer life at high V's within the and high velocities within the limits. Even in the increasing of this feed also raises the cutting forces, which leads to high energy requirement for the machining process. Hence, the cutting temperature also is an less effect in the case of increase in the feed, but this increase is unlike the V raises the surface roughness. Coming to the ways of this work environment aspects, environment is also one of the basic phenomena need to be characterized in the machining process, that the seasonal variations leads to an machinability properties variations also. The main purpose of this employing cutting tools is to improve the machinability characteristics by providing of these coolants, or we'll be calling the lubricants. The tool life will be getting increased, and surface integrity also will be increasing at an cutting zone, and hence the tool life and work part surface finishing will be very much favorable in situation that leads to an good dimensions occurrence in the machining process. Coming to the favorable ways of improving the machinability, so we're having many of the laggings related to different fields, either in the work part related, tool related, material selections related, and operational parameters related. So how to compensate this? The machinability of the working materials, whether it can be improved without sacrificing the productivity, if we have been followed some of the minute parameters as follows. First one is the favorable change in the composition or microstructure or even the mechanical properties by the combination of the amount of additive materials in the work and even the appropriate the heat treatment for inducement of the or strengthening of the materials. Hence, the better mechanical properties will be achieved to the particular material or alloy which we are being utilizing. And secondary, the proper selection and use of this cutting tool material and geometry, that is depending upon the work material, type of material which need to be worked or machined, and even the machinability criteria which need to be considered. Next, the cutting velocity, speed, feed, that will be directly based upon the tool and work part materials, leads to an optimum range, at an optimum range. Even by proper selection of the special techniques such as hot machining process, which leads to an greater than the precrystallization range of temperature, and cryogenic machining, which need to be operated at a negative range of temperatures, the machining conditions will be calling as an cold working processes, and even if feasible or economical, and must be an eco-friendly. These are the compensating or possibility ways, some of the possibility ways in order to improve the machinability, indeed to get the good surface finishing and the perfect dimensions of the material as per the vendor's requirements. So those are the basic steps to be characterized, and even the proper selection and appropriate method of applying these MQL processes such as lubrications over the tool and work part mating regions, the desires, the decreasing in the thermal stresses, and commencement of the good velocity ratio regarding the cutting. We will be saying as the cutting velocity will be maintained in an appropriate condition, and the concerned feed rates will be followed as per the strategies without having any hires in the frictional resistances or the coefficient of frictions, and that is also should be considered and major role. And in the dynamic conditions, so variations in the case of environmental aspects such as this hot machining process and cryogenic process need to be altered as per the eco-friendly. These are the steps need to be followed for getting the better accuracies over the machinabilities. By following those conditions, the machinabilities on ferrous metals and non-ferrous metals leads to some of the points that we'll be discussing in the next class. Thank you.